Example 21.2 part C and D wants us to find the exact solution as well as a decimal approximation for each of the given equations. We'll start with part C. 5 raised to the x minus 3 is equal to 137. This is an exponential equation, so I'm going to use the definition for logarithmic form and exponential form equivalency to convert this into a logarithmic form. So I'll start with writing log. The base is 5. The argument will be 137, and it's all equal to the exponent of x minus 3. Now to get x by itself, I would add 3 to both sides. I'd get log base 5 of 137 plus 3 is all equal to x. Now, one of the details in the instruction, it says express the exact solution in terms of natural logarithms. The reason why I would do such a thing is because log base 5 is not one of our frequently used logarithms. Those would be the common log and the natural log, and those are the two that are programmed into most every scientific calculator. So this is an exact answer, but to put it in terms of natural logs, we're going to use the change of base formula and write this as ln of 137 divided by ln of 5 plus 3 is all equal to x. And that represents the exact answer in terms of natural logarithms. And as far as the decimal approximation is concerned, you should get approximately 6.057. And there's our solution for part C. Part D is going to be a little more challenging. Part D doesn't have just one exponential statement. It has two, and it also has a third term with a constant. In order for an exponential equation to be converted into a log equation, there can only be one exponential statement. So the fact that there are two exponential statements here is going to make it difficult for us to be able to use that definition. But if I could somehow get it down to just one, then we would be in business. So one of the things that I want to mention, let me make a little note here about factoring. So for example, if I give you the polynomial x squared minus 2x minus 3 is equal to 0, that will factor using the trinomial factoring technique into x minus 3 times x plus 1. Same thing can be done if I had, for example, x to the 4 minus 2x squared minus 3 all equal to 0. That also will factor using trinomial factoring x squared minus 3 and x squared plus 1. And I'll do one more. If I was to take this and have x to the 6 minus 2x cubed minus 3 all equal to 0, that also will factor into two binomials as x cubed minus 3 and then x cubed plus 1. So there is something about trinomial factoring that allows this to work, and the relationship is with your middle term and the leading term. If you'll notice on the first example, the power on the x is 1 for the middle term and it's 2 for the second term. So the middle term is half the power of the first. Same thing ends up being true on the second example. 2 is half of 4, and then on the third example, 3 is half of 6. So as long as you have three terms where you have the powers being this related to each other, you should be able to perform trinomial factoring. So notice that on our equation we have e to the 2x minus e raised to the x. This is going to fit the condition for trinomial factoring. So to factor this, I'm going to make two binomials. Each one is going to be with e to the x minus 3, and then e to the x plus 1. Now the benefit to using the factoring approach is that then you can take each factor when it's equal to 0 and set each factor equal to 0 individually. So thus e to the x is equal to 3, or e to the x is equal to -1. And this fixes our problem. The problem we were having was that we had two exponential statements in that one equation. Well, now, because of factoring, we can split it into two separate equations, and each one of them only has one exponential in it. So now I can convert these to logs. Since the base is e, these are going to convert to natural logs. So this will be ln of 3 is equal to x, and then ln of -1 is equal to x. Now the ln of -1 is not going to be permitted because of the argument there. So the argument always has to be greater than 0 in order for it to be a working value for a logarithm. Since we don't have that, that one's not going to be a viable solution for us. But for the natural log of 3, that will be perfectly fine, and it is approximately 1.099.